So we're going to have a think about the function y equals 3 minus 2x all raised to the power of -1. You can see it listed on the left-hand side, and this is the graph of this function. Now, the whole idea of a binomial expansion is that it allows us to find an approximation for that particular function. So y equals 3 minus 2x to the -1, we can use the binomial expansion to find a series of terms which can be used to approximate this function. Now, because its power is -1, there would be infinitely many terms in its full expansion. It's an infinite series, and of course we can't write down infinitely many terms, so we just write down as many as we can. I'm not going to go through how to do the expansion here, that's covered in full detail in the other lesson videos, but what I'm going to do is write down the first 6 terms of the expansion. So here are the first 6 terms of the expansion, and as I said, we can use these as an approximation for the full function. Now, is the expansion a good approximation for the original function? Well, the more terms you use in your expansion, the better the approximation. But there is something else that affects how good an expansion is for an approximation to a particular function, and that's whether or not you are within the validity conditions. So an expansion in this particular situation for a binomial where the power is not a positive integer will only be valid for certain types of x value. Now, in this particular situation for our question, the expansion is valid for mod 2x less than 3, which of course is mod x less than 3 over 2, which can be written as x has to be between -3 over 2 and 3 over 2. Now, we can get an idea of this, a better idea of this numerically, by choosing an x value and seeing what happens when we substitute that x value into the original function here, and what happens when we substitute the x value into the 6 terms that I have of this expansion, and seeing whether the result from the expansion matches the true value of y. So the first thing I'm going to do is I'm going to choose an x value, and I'm going to choose an x value that lies within this validity condition here. So I'm going to choose x equals 1. Now, what I'm then going to do is I'm then going to substitute x equals 1 into the original function, which I'll highlight in bright green here. So if x equals 1, the true value of y is equal to 1 as well. And you can see that here from the graph, 1, 1. Now, that's the true value of y at x equals 1. What does the expansion give us if I substitute into the expansion, or the 6 terms that I have of the expansion? So if I substitute in, this is what I get. 0.912208 ... So that's from the expansion. Now, that's not a bad approximation for y equals 1. So this is really very close to 1, so not a bad approximation at all. So you can see when you choose an x value that's within the validity condition, then the value of y produced by the approximation, the binomial expansion, is very close to the actual value of y. So now, let's compare and contrast this with what happens when we choose an x value that's out of range. So I'm going to choose x equals 5, and I'm going to substitute that into the original function. So 3 minus 2 times 5 all to the power of -1, which gives me negative 0.142857. So a really small negative value, and we can see that here from the graph. Here's x equals 5, and can you see the y coordinate, if we traced across to the y-axis, would be a very small negative value. But what happens when we substitute into, again, the first 6 terms of this expansion? So I'm going to replace x with 5. And calculate this yourself, you might get a bit of a shock. You get 195.8203, and that is nowhere near the true value of y. So you can see, if you choose an x value that's not within the validity condition, the expansion, the binomial expansion, does not give a good approximation to the true y value, no matter how many terms you include in your expansion. So this is essentially what we mean by an expansion having a set of validity conditions attached to it. So you can expand all sorts of binomials, but the ones where the original power is not a positive integer will only be valid for certain conditions on x or certain x values. And we're going to have a look at this graphically now. So as you can see, the red graph again is the graph of y equals 3 minus 2x all to the power of -1. Now, the blue graph is the graph here, and it's the first 3 terms of the expansion. Can you see that there is a small part of the curve, and I'll highlight it in green here, for which the expansion and the original function match very, very closely. Once you go outside of that set of x values, though, you get massive divergence. Look at here to here. You can see the red function and the blue function are nowhere near each other. Again, here, the red function is absolutely nowhere near the approximation. And what you may notice is that this green section here, where the expansion matches the original function very closely, well, look at the set of x values. You've got minus 1.5 here, which is minus 3 over 2, and then over here you've got 1.5, or 3 over 2. So these are the validity conditions. So this set of x values is where you get a good match. Now you may be thinking, well, what about over here at 3 over 2, where you perhaps don't get as close a match? Well, remember, there are only 3 terms here. So if you're only using 3 terms of your expansion, you may not get as good a match even within your validity condition. So we're now going to have a look at another pair of sketch graphs where we've included more terms in the expansion. So here we go. Can you see we've now got 4 terms in our expansion? So let's look at the validity condition again. So -1.5, 1.5. Again, within that set of x values, you get a very, very close fit between the 2 curves. But when you move outside of that validity condition, you get very, very wild divergence, and they don't match closely. So in this example here, we've now included 5 terms in the graph of the expansion. So again, if I find -1.5 and +1.5, can you see the fit is even better at the endpoint 1.5 here? So the more terms you include in the expansion, the better the approximation is as a match for the original function, or the better the expansion matches the original function, but only within the set of valid x values. Again, we get a divergence here and here, and they don't match here and here as well, outside the valid values of x. So this is my last example here, and we have 6 terms in the expansion. So again, let's look at the comparison between the graph of the 6 terms of the expansion and the original function. So again, at the endpoints, -1.5 and 1.5, we get this very nice fit between the 2 curves, but we get divergence outside of that range, here and here, and they don't match. So this is what we mean by an expansion only being valid as an approximation for the original function for a certain set of x values, which we call the validity condition. And if you are expanding a binomial of some sort, ax plus b raised to the power of n, if n is not a positive integer, then you must ensure that you understand what the validity conditions are for your expansion.